We are Group 10 and today we will talk about our project. We have been asked to create a pregnancy test for visually impaired women as currently on the market there are none available. The only existing methods require some apps that are able to describe everything that appears in front of the camera, or a video call with a volunteer that could tell the result. At the moment, around 139 million women suffer from visual impairment, a number that will dramatically rise in the following 25 years given the statistics. For every woman, the output of the test can lead to different moods and feelings. The joy or the displeasure generated by such an experience should be kept private and shared whenever the person in cause feels comfortable. Our project will help women to feel autonomous and confident, especially in a moment where they might feel most vulnerable and emotional.
We decided to run a survey in order to get an insight of how important it is for a visually impaired woman to be able to use a pregnancy test by herself. All the women we surveyed agreed that using a pregnancy test without needing someone else's assistance would be life-changing. We want to create a product that can be used without help from other people, as we understand this need of feeling in power and of privacy. This device might not seem for some essential, but making people feel happier and more comfortable should be a priority as well. Also, we want all women to have the same authentic experience when using a pregnancy test, whatever their inabilities might be. When we were first presented with the project, we came up with many ideas. A machine learning mobile app that scans a traditional test and reads out the result. A test that indicates results by warming up or cooling down. A test that says the results out loud. A test that shows the result through a mechanical change that can be felt by hands. A funnel or a cap with a built-in test inside for easy collection.
Survey revealed that having a similar experience to a standard test was of paramount importance. We discarded the machine learning app. Moreover, our target users valued hygiene and discretion very highly, so we eliminated the test with the incorporated cup or funnel, since it couldn't be carried comfortably in a handbag or shown to others afterwards. Based on the survey, an audio output is the preferred method of communicating the result. Since 2% of the population are affected by visual and auditory impairments, we wanted to make this test accessible to all visually impaired women, so we felt we could not purely rely on an audio system. The mechanical feedback was the second highest preference from the survey, therefore we continued to combine the two communication methods. Our other requirements are: communicate results privately to allow its use in a public bathroom. To ensure this, we added a button so they can choose to hear the result when they are alone. Ease of urine collection. For this, we added a cup into which the stick can be dipped. To be accessible to all women who might need this product, we set a price limit of £15. Packaging is waterproof and the test is splash-proof. We designed a portable size and weight that can be discreetly carried in a handbag with dimensions and weight similar to that of a standard test, and the result should be able to be checked repeatedly to assure user did not misinterpret their result.
Here is a demonstration of the finished product. First, the user will take off the watertight cap, then dip the strip's absorbent end into a cup of urine. Once the result has been processed, the motor will automatically spin to display the tactile plus or minus sign so that the result can be felt. For added assurance of an accurate reading, when the user has moved to a private space, they can push the button and hear the result auditorily. Our design takes advantage of the tried and tested chemical component of existing pregnancy strips on the market. Urine is drawn up a lateral flow immunoassay test, and through a series of chemical reactions, colored lines will appear according to the HCG concentration in the urine, showing a positive, negative, or an invalid result. Our device will have one of these strips inside, and then scan the lines for a digital result. Our innovation lies in the method of communicating this result to the user, through auditory and tactile senses rather than visual. The main idea is based on the following tasks which needs to be done: reading the lines, processing the information, and displaying the result.
During the electronics labs, we tested several ideas by using photoresistors and phototransistors, and the result of our analysis showed that the phototransistor is more sensitive to light, so it is more suitable for our design. LEDs and phototransistors will be mounted on a PCB board as shown. The red LED's light will reflect off of the strip and will be detected by the phototransistors. When the colored lines appear, they will absorb more light, making it darker for the phototransistor beneath. So the output of phototransistor 1 and 3 indicates the presence of a line, while phototransistor 2 acts as a control. So once it's calibrated, this setup will allow the lines on the strip to be understood by the microcontroller as a positive, negative, or invalid result. For example, this diagram shows the case of a negative result, while only one colored line appears. The amount of light detected by phototransistor 1 and 3 will be different. This is interpreted by the code as negative.
For auditory part, we are using a buzzer, which will play a long continuous sound for a positive result or multiple bits for an active one. In order to maintain privacy, our pregnancy test will include a button that will control the playing of the sound, so the user can choose when and where to play the results after she takes the test, and she will be able to listen to the results again by pressing the button.
We have assessed a few designs for the tactile output. The first design is based on a DC motor. A cube with positive and negative sides would go up and down depending on the input current received, using a screw mechanism. However, a DC motor is not suitable for achieving a specific amount of rotation, so it cannot ensure the cube will move to an accurate position. The second idea is that the motor will rotate anti-clockwise or clockwise according to the input current received. Then one of the legs connected will extend outside the casing and display the result. However, this design is too fragile. The third idea is using a motor with positive and negative sides on its two flaps. There is a window cut on the casing. The motor will rotate, and the cracked flap will move to the window so it can be felt. The issues are that the flaps could be too small to be felt, and the window is not splash-proof.
In our final design, we are using the servo motor. The motor stays at 0 position at the beginning with a line indication. After the user takes the pregnancy test, the motor would turn 90 degrees with plus sign indication representing positive result, or turn negative 90 degrees with minus sign indication representing negative result.
It moved. Positive.
So when it beeps like that, it means positive.
Negative, it moves back. Positive here.
This is positive again.
And then if I cover one of them, it's negative.
Correspondingly, we built a cube that can be connected to the motor. When the motor rotates, the cube rotates with it. The plus and minus sign indication is built on the cube for displaying results as positive or negative. In addition, we will have a cap protecting the testing strip.
For the main body of the pregnancy test, the outer casing, there is a rectangular shape cut out at one end and a circular shape cut out at the other end. These are designed for the testing strip and a rotational cube respectively. There is an arrow-shaped bump on the outer casing which indicates to the user which result to read on the rotational cube. Arduino is one of the most powerful microcontrollers that is available to us. We have used Arduino Uno to drive our hardware. We closely cooperated with the hardware team throughout the whole programming process to exchange our ideas as well as implement them to create a functioning device. The programming tasks were first done separately, based on different components including coding the buzzer, phototransistor and the servo motor. Afterwards, the codes were sutured together and we carried out tests using the hardware components.
We're also thinking about integrating our circuit on a single PCB, so the selection of microcontroller is another important process in our project. The selection process of microcontrollers follows the 3 key principles. The first one is code functionality, which means the microcontrollers should be capable in data processing exactly the same as what we have achieved already. The second one is codes should be transferable. This will enable us to easily transfer and maintain Arduino programs in our new microcontroller. The third one is the overall cost should strictly fit the demand in our PSD. We found the chip 80MEGA328P is a strong candidate among the microprocessors. They are the chips used on Arduino Uno, and so far we have built a standalone Arduino based on the breadboard to evaluate the applicability to our project. Before launching the manufacturing process, we plan to evaluate the functionality of our device. More specifically, we want to check that our device meets the needs of its users in an efficient, safe, and convenient manner.
Most importantly, we will confirm that our device can detect pregnancy accurately. We will test that our device shows negative results for concentrations below 25 milliunits per milliliter and positive for concentrations above this value. The correct functionality will be checked by selecting 5 volunteers. We will test that our device can communicate results at least 5 times over a minimum of 12 hours. The tactile output should not change even under external forces, and the auditory output must still work at an appropriate volume every 2 hours. Our device and its packaging is designed to measure 6 by 6 by 18 centimeters and weigh 100 grams at maximum in order to ensure that it can be transported easily and discreetly. We will test the durability by performing a drop test from 3 meters. Even though a pregnancy test seems rather harmless, the safety of the user still needs to be taken into account throughout the design and manufacturing process.
So how did we make our design safe? Firstly, we have designed the casing to be smooth with no sharp edges or corners. Our test also includes some electrical components. Therefore, we made the casing out of plastic, which establishes a very low risk of electric shock. The casing of the test has also been tightly sealed so that little to no liquid can come into contact with the electronic part of the test. The strong seal will also prevent the device from breaking easily. And finally, we will make sure that the circuit and its components do not overheat while connected. How will we ensure the user's safety during manufacturing? Firstly, before we begin manufacturing, we would have to do further testing to ensure that the electromagnetic emissions from the device is in compliance with regulations for in vitro diagnostic medical equipment. Then during manufacturing, we would place the product in sterile packaging to protect it from contamination. We would display appropriate warnings and safety guidelines in English and Braille on the packaging and in the user guide. And lastly, we would put our pregnancy tests through quality control checks to verify that they are safe. In the future, we could improve our design by 1. Using an auditory output with spoken recordings of the words positive and negative to make the result easier to understand. 2. Our test should be made more waterproof as there are still some small gaps where liquid may enter into the casing. And 3. We should also try to reduce cost as our pregnancy test may be expensive due to the servo motor.
In acknowledgement of these drawbacks, we may in the future consider adapting our design to make the device reusable. This means the cost per usage would reduce, but the device would have to be more waterproof than our current design in order to be hygienic. For example, the reusable test could have a casing made of 2 vase-shaped parts in a rotating cube. This would deflect water away from the longitudinal axis of the device when it is rinsed, such that water will not enter the casing. This test could have a latch that is lifted to insert the test strip. The latch should be attached to a spring that resists rotation, so that it is able to open to 90 degrees and return to the closed position once released. The testing strip could be adapted to be thicker at one end, to prevent the strip from falling out of the device, and for users to distinguish which end to insert into the slit. The extra thickness of the strip should be made of a non-absorbent material to prevent the flow of urine from being reduced. We could design the slit where the testing strip is inserted to be transparent and intact. This would allow the phototransistors to detect lines on the test strip while preventing urine from coming into contact with the circuit. This Gantt chart shows our progress from the start of the labs and our future plans until the end of the project.
We're Group 10.
And we're working hard to bring you this product.
Thank you for watching.